Welcome back to The Explainer. Today, we're setting the stage for a seriously epic, high-stakes showdown. On one side, we've got traditional, human-made math equations. And on the other, the absolute raw processing power of artificial intelligence. The battlefield here is a multi-billion-dollar industrial crisis. We're going to explore exactly how scientists are using AI to predict totally eco-friendly solutions to industrial corrosion. So get ready, because the way we discover new materials is literally changing right before our eyes. Now, to really grasp the stakes here, we have to look at the massive real-world impact of industrial corrosion. When metals break down in high-stress settings, the consequences are catastrophic. We're talking hazardous chemical leaks, major failures in energy infrastructure, destroyed pipelines, and just staggering financial losses. But here's the massive catch. Historically, to stop rust in these super harsh environments, industries have been forced to rely on highly toxic chemical inhibitors. So the big question driving today's explainer is this: how do we stop rust from destroying our critical infrastructure without poisoning the environment in the process?
Section 1. The Global Corrosion Crisis and Eco-Friendly Heroes.
All right, let's just dive right in. This global corrosion crisis is basically a ticking clock, especially in sectors like oil and gas, refineries, and chemical processing. You see, these industries rely heavily on carbon steel and stainless steel pipelines to transport liquids and gases under absolutely extreme pressures and temperatures. And during routine maintenance, things like acid cleaning, these pipes get exposed to highly aggressive, corrosive environments. For decades, the rust inhibitors they used were packed with harmful, toxic substances. But with stricter global environmental policies popping up, the race is absolutely on to find completely green alternatives. Take a look at the complex molecular structures mapped out right here. These are our new eco-friendly heroes. They're a class of organic compounds called 1,2,4-triazole derivatives. Researchers have pinpointed these specific molecules as incredibly promising, non-toxic rust fighters. The best part? They don't rely on rare, super expensive metals like platinum or gold. Instead, they actually form stable protective complexes right on the surface of mild steel, basically acting like a microscopic shield against those harsh acids. So why are scientists so completely obsessed with these specific triazole chemicals? Well, first and foremost, they're non-toxic and environmentally safe, which obviously checks a massive regulatory box. Second, they are thermally stable. That means they won't just break down when things get incredibly hot inside an industrial refinery. Third, they're actually pretty inexpensive and easy to synthesize. But the real kicker? Experimental studies show they have a jaw-dropping corrosion inhibition rate, ranging anywhere from 73% all the way up to 98.5%. They're cheap, they're green, and they literally stop rust dead in its tracks.
Section 2. The Prediction Bottleneck.
Now, discovering that a chemical might work is one thing, right? But proving it, that's a whole different story. Traditionally, testing these incredible chemicals requires physical lab work, using slow methods like weight reduction or electrochemical impedance spectroscopy. This means physically mixing chemicals, treating the metals, and then waiting weeks just to see what rusts. It takes a tremendous amount of effort, specialized instruments, and time. It is frustratingly slow. If we have hundreds of potential green chemicals to test, the physical lab just cannot keep up. So to bypass this massive bottleneck, scientists turn to a really brilliant theoretical concept called QSAR. That stands for Quantitative Structure-Activity Relationship. In plain English, it's a method where scientists try to mathematically map a chemical's real-world success before a single drop is even mixed in a beaker. By strictly looking at a molecule's structure and its quantum properties, researchers try to predict exactly how well it's going to perform as a rust inhibitor. To actually make these mathematical predictions, scientists have to hunt for micro-level data, or what we can call quantum clues. They calculate specific parameters, for instance, EHMO, which is the molecule's potential to send or donate electrons. Then there's LUMO, which is its potential to receive those electrons. They also look closely at adsorption energy, which basically measures how well the chemical will spontaneously stick to a metal surface, like iron. All these tiny, completely invisible quantum forces dictate whether our eco-friendly triazole will successfully bind to the steel and form that much-needed protective shield. Section 3. The old versus new duel. But here is the tricky part. How do you take a bunch of complex quantum clues and actually turn them into an accurate, real-world prediction? That question right there sets up the core showdown of our explainer today. It's a fierce competition between two radically different ways of analyzing data. Let's meet our contenders. On side A, we've got traditional nonlinear math equations. For years, scientists painstakingly crafted these complex formulas to try and link those quantum clues to actual rust prevention. And it was the best we had, but the predictions were often a bit muddy. Then, on side B, we have the challenger, an artificial neural network, or ANN. This is the raw, unfiltered processing power of machine learning, completely designed to recognize incredibly intricate, hidden patterns in data that human-made equations just completely miss. And this brilliantly illustrates the exact digital pipeline the researchers built to set up the fight. Instead of just randomly throwing chemicals at a wall to see what sticks, they built a highly structured workflow to move from simply drawing molecules all the way to running complex, predictive algorithms. Let's break down this procedure super simply. Step 1, the researchers drew out the 1,2,4 triazole molecules digitally and optimized them using a quantum chemistry technique known as the B3YP method. Step 2, they extracted all those juicy quantum parameters, the HOMO LUMO, and the sticking energy, straight into an Excel spreadsheet. Step 3, they imported that beautifully structured data directly into MATLAB, which is a really powerful high-performance computing environment. And finally, step 4, they hit go. They fed all that data into the waiting artificial neural network to see if it could somehow learn the secret formula for stopping rust. If we dive into the AI's architecture here, we can see exactly how it processes those 9 specific inputs, our quantum clues. It pushes them through 10 hidden layers of artificial neurons before finally spitting out one single output, the predicted inhibition efficiency. And it's kind of funny. We hear so much these days about AI writing our emails or generating weird art, but it's pretty incredible to realize that this AI is down in the microscopic trenches doing the really gritty mathematical work of fighting industrial rust. Section 4, the final verdict. All right, the data was processed. The network was trained. The old mathematical models were tested against the exact same data. And it all comes down to this. Treat these numbers kind of like a high score in a video game. Notice the correlation score, or R, right there in the center column. A score of 1.0 means a perfect, totally flawless prediction. Now, the traditional nonlinear math models scored an admirable 0.888. Not bad. But what's really interesting about this is the artificial neural network. It made a massive leap to a 0.967 correlation. It didn't just edge out the old human-made equation, it absolutely crushed it. This proves that the AI can map the relationship between quantum data and rust prevention with near-perfect accuracy. And hey, if you want to see just how accurate it is, look at this incredibly tiny number. 9.81 times 10 to the negative 5th power. That right there is the mean square error of the artificial neural network. It represents a truly dramatic drop in the error rate compared to the old methods. What this microscopic scale actually proves is that the neural network is successfully learning these deeply complex, nonlinear chemical relationships that traditional equations just completely gloss over. It's literally finding the invisible threads that tie molecular structure directly to real-world performance. To truly appreciate this level of accuracy, follow the red line you see mapped out here. Notice how beautifully tight those red predictions align with the actual physical laboratory results. Those are the dark squares. The AI's predicted numbers track the real-world lab results almost perfectly. It's amazing. It proves, beyond a shadow of a doubt, that we can now trust a computer to tell us if a chemical will stop rust without ever having to wait weeks to test it in a physical lab. So what does this all mean? Let's connect this data right back to the big picture. This explainer isn't just about a computer getting better math scores than an old clunky formula. It is about rapidly optimizing safe industrial solutions. By using AI to totally shatter that prediction bottleneck, scientists are now fast-tracking the discovery of cheap, green, highly effective materials. Think about it. We can now screen thousands of eco-friendly chemicals digitally, find the absolute perfect rust inhibitor, and deploy it to protect our energy infrastructure and our environment in a fraction of the time it used to take. We've seen today how an artificial neural network took incredibly complex quantum data and basically perfectly predicted a green solution to a multi-billion-dollar industrial crisis. And it really forces us to look ahead, doesn't it? If machine learning can perfectly map the quantum behavior of a rust inhibitor today, what life-saving, eco-friendly material will it discover tomorrow? The digital laboratory is officially open, and the possibilities for our future are absolutely endless. Thanks so much for joining me today on The Explainer.